Our next session, featuring our own Dr. Alicia Frame, is just about to start. If you have questions during the presentation, please submit them via the Questions tab. And without further ado, here's Lance Walter, CMO of Neo4j, to introduce the next session.
I'm really excited to bring you this next talk. It's actually from the recent Open Data Science Conference, presented by our own Dr. Alicia Frame. The session was extremely well received by that audience, so we were excited to be able to offer it to you today. And as I mentioned in my opening comments, we do have live experts online, including Alicia, during today's session. So you have the rare opportunity to ask questions of the expert speaker while she's actually delivering the talk. So please take advantage of that. Dr. Alicia Frame is lead product manager for data science at Neo4j and has been with the company for 3 years. She has a PhD in biology and computer science from UNC Chapel Hill and spent years doing data science research for organizations like the Environmental Protection Agency and the USDA. She works closely with our customers to advance our strategy and offerings for analytics and graph data science. Dr. Frame's sessions always get high marks from our audience, and her experience is particularly relevant to this topic. So let's get rolling. Welcome back to Connections, Alicia.
Hi, I'm Alicia Frame, the Director of Data Science at Neo4j, and today I'm here to talk about how relationships matter, or how you can use connected data for better machine learning. And before I dive into any of the technical details, I like to kind of have a simple thought experiment. Everyone knows the saying, it's not what you know, it's who you know, and we like to add on where they are. So if you think about how you got your last job, was it because you went to a specific university, or you had a specific degree, or you had a certain number of years of experience doing a specific thing? You know, kind of your typical rows and column descriptors. Or was it because a former colleague told you about an opening at their new company, or a mentor you had helped you revise your resume so it was more relevant to the position? Or was it, your college roommate's friend's brother happened to know about an open position that wasn't posted yet? The idea is that the relationships between you and other people are just as important as the columnar descriptors you'd normally think of. And it's true in this toy example, but it's also true in the real world. So network structure, in this case that I just talked about, is actually really predictive of pay and promotions. They've done studies looking at, you have a social graph, who interacts with who, who's on which team, who knows who, of people at a company. And they found out that the connections between people were just as predictive, or highly predictive, of what happened in their careers. People who were near structural holes or organizational misfits in our graph topology tended to be much more likely to get raises or promotions. The structure of their social networks at work were much more important than the work that they were doing. So connections matter. And it's not just this example, right? We know relationships are some of the strongest predictors of behavior. If you look at how do you predict who's going to vote, well, it's not, how much money someone makes, or their party affiliation, or their age. It's actually how many of their friends or social connections voted. If you want to predict who a smoker is, probably all of you are data scientists and you're thinking, well, what's their age, race, gender, educational attainment, where do they live? It's actually how many people they know in their social circles are smokers. Relationships are incredibly strong predictors. But you can't make predictions on data you don't have. So most data science, probably what you're familiar with, ignores relationships, or maybe you can hand engineer, a one-hop relationship. Graphs, on the other hand, are built around relationships. We treat relationships as just as important as your rows and columns or your data points themselves. So the TLDR of this talk is you don't have to guess at correlations between your data points anymore when you use a graph database like Neo4j. With graphs, the relationships between your data points are first-class citizens. They're inherent, they're analyzable, and you can start to make predictions not just based on rows and columns, but the connections between your data points. And this isn't just, Neo4j, the graph database company, making up new uses for graphs. Gartner recently published, the 2020 top trends in analytics and AI. And they said that graphs form the foundation of modern data and analytics. They truly believe that the future of data science is graph. In another survey, they said that 92% of companies were we're looking to deploy graph technologies in the next 5 years. So there's an understanding that being able to connect data points to each other, being able to understand your data in context, and being able to use the connections between data points is super valuable in data science. And it's not just analysts. If you look at the number of research publications, AI research papers featuring graphs, so anything from graph algorithms, network science, graph embeddings, the number of papers published per year has skyrocketed in the last decade, going from 205 to over 6,500. And we've also seen this increase in interest at Neo4j. If we look at the graph algorithms book that we published in 2019, we have over 160,000 downloads. We've seen a 4 times increase in traffic to our data science pages. We've seen a 3 times increase in the number of data scientists who are registered on our community forums and our databases. So it's an industry trend, it's an academic trend, and it's a trend that we're meeting at Neo4j. So who is Neo4j? Some of you are probably familiar with us. Some of you probably this is the first time you're hearing of us. Neo4j is the Graph Company. We are the creators of the world's leading graph database. We invented the concept of the labeled property graph. We're the first enterprise-ready graph data science platform. We're the most flexible graph data model, so we're schema optional, which means you can connect concepts to each other without worrying about the architecture. And we have the easiest to use graph query language, Cypher, so that you can express the patterns you're looking for and find those in your data. There are thousands of companies using Neo4j, everyone from FinServ to retail to software vendors like eBay, Merck, UBS, LinkedIn. We have offices in Silicon Valley, Malmo, London, Munich, Paris. We're pretty big in the graph world, and what we're about is figuring out how people can make sense of and use connected data. So to take a couple steps back and really talk about what do we mean when we say graph, what do we mean when we say graph database? We don't mean a bar graph or a scatter plot. Those are charts. What we mean is a graph of connections. You can think of it as networks. So maybe the easiest one to reason about, and what I talked about in the beginning, are networks of people. You know, you have your social graph. That's how Facebook and LinkedIn work, right? People know each other and you can reason about that. Then, as you get more sophisticated, you can think about things like transaction networks. Maybe you have people buying items and returning items and looking at items on a website. And you want to make predictions about what they'll buy next, who's going to return something, or what's the best supply chain. Getting even more sophisticated, we talk about knowledge graphs, right? Where you're linking concepts. So soccer is a sport. A person can play a sport. That same person can live in a country. You're connecting heterogeneous ideas to each other in context of how they're all related. And the common thread between all of these examples is the connections in these data sets. The relationships between those nodes are just as important and just as informative as the raw data points themselves. So we really like to say that graphs are everywhere. And so if we want to understand what is a graph, when someone at Neo4j says, you know, we're a graph database, a graph is really pretty simple. You have nodes, and I think of those like nouns. They represent entities in your graph, and they have labels. In this example on the right, we have person nodes and car nodes. And then your nodes are connected to each other with relationships. Each relationship has a type. So a person can love another person, or a person can drive a car. Love and drive are the relationships. And I think of relationships like verbs. So you have nouns connected by verbs. And nodes and relationships, both of them can have properties that describe them. So on a node, you've got your person, they have a name, they have a birth date, they have a Twitter handle. On your relationship with drives, you have the start date of their driving relationship. And these are key value pairs. So a graph is really just a way of connecting up nouns, concepts, with each other by way of relationships, verbs. And it's just a formal way of structuring your data in a way that you can query and analyze it. So what's graph data science? I talked about Neo4j, we're a database company. What does this have to do with data science? And when we think about what is graph data science, it's really, rather than just crunching numbers in rows and columns, graph data science lets you analyze the data relationships and structures, the connections between your data points, to produce answers, insights, and predictions. And so if we think about the toolkit that a graph data science has at hand, it's really three things. At the foundation is a graph query. So you can store your data in a graph. You can write a query to find a pattern in that graph. So if we think about the example of fraud. So I have accounts that make transactions with each other. And maybe I want to find out who's likely to commit fraud. I have an account, and I want to know how many accounts are there within 3 hops. So account transacts with account, transacts with account, transacts with account. How many accounts in that network have been labeled as committing fraud? So I've come up with a graph pattern that I'm going to match based on domain expertise, and I can pull that out of the data. Basically, I know what I'm looking for, and a graph query helps you find it. Then we have graph algorithms, and what these are is basically unsupervised machine learning techniques that help you find patterns in your graph. So maybe you want to know which parts of your graph are more connected to each other than the rest of the graph, or based on the structure of your graph, which nodes are most important. The graph algorithms let you do this at scale. You can do this either for feature engineering for an ML model, or maybe you just have a simple question. You want to know who's the most important node in this social network, or how many communities are there in this item co-purchasing graph. You run a graph algorithm to answer that. And then kind of rounding everything out, we talk about graph visualization. And this comes into play when maybe you want to explore your data visually. You want to see what's connected to what, traverse your graph, learn more about it. Or maybe what you want to do is share your results with coworkers, maybe who aren't as familiar with graphs as you. So we have visualization tools like Bloom or Curious that let you traverse your graph, explore, find patterns in your data, and collaborate. And taken together, all of these are techniques within the graph data scientist's toolbox. So when we talk about graph data science, it's important to talk about it on a spectrum from local to global. And I kind of covered this when I talked about algorithms versus queries. But on the local end of the scale, you know what you're looking for and you're making a decision. So you write a query. It's real time. It's about local decisioning and pattern matching. So find me how many nodes are within 3 hops who've committed fraud. I know what I'm looking for and I find it. And that's what you do in Cypher. At the other end of the spectrum, we talk about global computation, where you want to reason about the whole graph at once. So you're doing global analysis, you're iterating over the whole graph, and you're learning the structure of the network, updating your data, adding more information, or making predictions. So if you run an algorithm like PageRank, what you do is you calculate the PageRank score for each node in your graph, and now you have more data than you had before. Taken together, you can do both of these in the data science space. They serve different purposes, but this talk is going to be focused much more on the global side of this spectrum. And kind of the TLDR of like, why use graph? Am I just making everything more complicated? Is really graphs let you make better predictions using the data you already have. So the data science models you're using today probably ignore network structure. They ignore the structure of how data points are connected to each other, not at one relationship, but at 2, 3, 4 hops, that extended topology. What graphs can do is they add highly predictive features to your ML models. So we have a graph. This is just a screen grab from Bloom on the bottom left. And you can see you could extract features from that graph. Maybe you calculate the betweenness centrality, or you run a Cypher query to find the unique people sharing an identifier, or you add a score to your graph. Each of those is a new graph-based feature that you've extracted, and you can append to that table of rows and columns that describe your data. Then you can make predictions not just about your tabular properties, but about that graph topology, about those important predictive relationships. The other thing you can do with graphs is you can make otherwise unattainable predictions. So a really classic use case of graphs in data science is you have a knowledge graph and you want to do knowledge graph completion. So maybe you're going to do link prediction. If you don't have a graph, if you're not treating relationships like first-class citizens, how can you predict your graph structure? So graphs let you both improve the existing pipelines you have or make new and different predictions. So I think they're pretty useful. So how do we do it? When we talk about graph data science at Neo4j, we talk about our graph data science framework. And there's 3 parts to that. We have the Neo4j database, which stores your connected data in a graph shape, lets you query it, persist it, store that data so you can come back to it. On top of that, we have the graph data science library, which is what I'm going to be talking about today. This is your scalable graph algorithms in your graph analytics workspace. This lets you take that underlying database, identify the right subset or transform it or create different iterations of it, pull that into memory, and then run algorithms at scale against that slice or permutation of your data. And then remember we had 3 pieces in that Venn diagram in the beginning. We have Neo4j Bloom, which lets you do visual graph exploration and prototyping. So I've got my data in my graph database, I've enriched it with graph algorithms, maybe I've made some predictions, then I want to share it with my team, or I want to just explore what I made and does it make sense? I can use Bloom to interact with it and understand the connections visually. So when we talk about graph data science, it's really a journey, starting from simple queries all the way up to advanced machine learning. So if we think about a cipher query, what we're really talking about is a human-crafted query with a human-readable result. So I have to write that cipher query based on my domain expertise, but the results of that query mean exactly what I expect them to. So in my example here, I have match a person, find their enemy, and then find an enemy of that enemy, and then make the enemy of my enemy my friend. So the first person and the last person, I merge them to make them friends. I wrote that query based on, supposing that a common enemy makes people friends, and then I can read the results. When I get it back, I wrote the query, so I knew what I was looking for. Building on that, we talk about graph algorithms, and what these are is, traditional network science techniques that have a predefined formula, and they give you a human-readable result. So my example on this side is PageRank. Larry Page invented that in the 90s. It was how Google worked. It was how do you figure out which website is most important? And you calculate that by iterating over every node and all of their neighbors and all of their neighbors' neighbors to come up with a score. There's a formula, but you get a result. In a social graph of my company, our CEO, Emil, could have a PageRank of 13, and I have a PageRank of 4. That result is human readable. A higher PageRank is more important. Our CEO is more important than I am. You could run a community detection algorithm, and if 2 nodes have the same community ID, they're in the same cluster in the graph. So there's a formula that's being calculated, but the result is human readable. Kind of the next level of sophistication is a graph embedding. And what this is it's an AI learned formula. So instead of saying, calculate the number of neighbors every node has and the number of neighbors its neighbors have, you have a heuristic that you learn to fit a function. So in this case, my screen grab is GraphSAGE. It's for embedding generation. And there's a way that you learn that embedding, but that embedding is custom to your graph and you tune it for your problem. And the result you get isn't, a single number. It's a fixed length vector. And if I look at them, all I can say is, well, it looks like Emil, Amy, and I have different embeddings, and so that's something, but it doesn't necessarily make sense. However, if I wanted to take that vector and put it into my ML model, I've learned what's important about my graph in a machine-readable way. So it's a really powerful feature engineering technique. I can capture the topology of my graph in a way that my ML pipeline can learn about it. So you kind of build up for sophistication, and any of these can be used as an input to your machine learning workflow, where then you're going to train a model based on the results of your queries, algorithms, or embeddings. Today, I'm going to really be talking mostly about graph embeddings and how you can do supervised machine learning in Neo4j. So historically, if you've heard someone from Neo4j talk about graph algorithms or graph data science before, you've probably heard us talk about the graph data science library. There's 6 categories of unsupervised machine learning algorithms covering a whole bunch of different tasks. And these are what people think of, right? You have pathfinding and search, which is given 2 nodes in my graph, what's the shortest path between them? What's the best path between them? Is there a path? How many paths are there? And we really see these typically used in an analytics use case looking at routing, logistics, supply chain questions, really around, can I traverse my graph? Can I connect these 2 nodes? we have the community detection algorithms, and what these are is algorithms that cluster your graph based on nodes that are more connected to each other than the rest of the graph. So if you've done KNN on your tabular data, these are kind of similar techniques except applied to relationships, and you find clusters in your data or partitions. We have similarity algorithms that let you evaluate how alike two nodes are based on their neighbors in the graph, based on their properties, or based on their relationships. And so given a node, you can find the most similar node or nodes in the graph. We have the centrality and importance algorithms, and what these do is they figure out how important nodes are based on a bunch of different equations. So you could have PageRank or betweenness centrality, and PageRank finds transient influence, betweenness centrality finds bridge points. They're different ways of defining importance, but you might want to use this if you're looking for influencers or looking for risks. So a node with high betweenness centrality, if you remove it from your graph becomes disconnected. In a reliability use case, you probably don't want to remove that node. And then we have the link prediction heuristics, and these are different than the supervised ML algorithms I'll talk about later on. But basically, they take a pair of nodes and they look at the topology of the graph around those nodes and estimate the probability that they should be connected, something like common neighbors or Ademic Adar. And then kind of the transition point between your unsupervised network science techniques and your kind of much more traditional supervised machine learning, we have the graph embeddings. And basically what these are is they learn from the structural information of your graph, a way to represent your graph in lower dimensional space, and then you can use that for machine learning. In Neo, we have over 50 robust algorithms, and we also have the analytics workspace, which is how you reshape your graph for data science. So to spend a little bit more time on graph embeddings, because I think these are kind of the newest concept in the library, they're basically a way of representing each node in your graph as a fixed length vector. So if I have a 5 billion node graph, I want to represent it in a way that I can do machine learning on it. If you think about your graph as like an adjacency matrix, you'd have 5 billion by 5 billion, one row, one column for each node, and you'd have a 0 or a 1 if they were connected to each other or not. The problem with that is each node would have a 5 billion long vector describing the node, and all it would capture would be its first degree neighbors. And it would be mostly zeros, super sparse. So in order to really do ML on your graph topology, you need to condense that information down into what's really important. So the embedding reduces the dimensionality of that giant adjacency matrix into a way that you preserve the key features. What nodes are neighbors of each other? What nodes are in the same community? What nodes have the same labels? And it's just in a smaller, much more compact representation where you learn what's important. And the way you evaluate if your embedding is any good is it can be decoded to reconstruct your graph or reconstruct a node label. So the idea is each node in your graph gets embedded into a fixed length vector that you could then use to decode the neighborhood around your graph, around your node, or decode the node labels or any other kind of task. And the idea here is you translate all of that rich extended topological information into something that you can reason about in an ML pipeline. There are different techniques used to represent different aspects of your graph. You can have node embeddings, whole graph embeddings, relationship embeddings, path embeddings. What we offer in Neo4j are node embeddings. And there's just different approaches to learn that representation depending on your use case. So two of the simpler techniques you can use are node-to-vec and fast-RP. And so node-to-vec is often the first embedding folks have heard of. And what you're doing with node-to-vec is for every node in your graph, you take a fixed number of random walks, so random traversals of your graph from that node, and you build up context. Basically, they're like sentences. So I have this node, I have its neighbor, the next neighbor, the next neighbor. And once I have all of these samples for each node, you train a skipgram model. And it's exactly the same way that word-to-vec works. And basically, you say, given a node, given these context windows, can I predict what the next node should be? And the embedding is the hidden layer in that skipgram model. And so the reason people like node-to-vec is it's pretty intuitive, it's pretty easy to explain. And the hyperparameters, the way you tune node-to-vec, are really easy to understand. Basically, how far should you walk in the graph? Should you stay close or wander far away? How many walks should you take? So it's really easy to wrap your head around what Node2Vec is doing. The problem? Node2Vec is slow. So we have FastRP. What FastRP does is you project a similarity matrix. So instead of that 5 billion by 5 billion matrix, you have a 5 billion by 5 billion matrix of pairwise similarities. You multiply that by a special vector of random numbers following an IID random distribution, and what you get is your random projection, basically your low-dimensional representation. It's up to 75,000 times faster than Node2Vec, but it has equivalent accuracy once it's been tuned. So you can control basically how the similarity matrix is constructed, how you weight different layers of the model. And it's really flexible to tune. The reason it's not everyone's first choice is those hyperparameters aren't super intuitive. It's hard to know what they mean, but because it's so much faster, you can generate lots of different FastRP embeddings and then figure out which one is most predictive of your outcome. Both of these, though, produce fixed length embedding vectors, so every node in your graph is going to get a set number of numbers that describe it. So every node in your graph gets a 100 number long vector that's its embedding. If you add new data, you have to retrain your embedding. So these are direct techniques. Every node gets an embedding, new data, retrain the whole thing. This might be annoying or problematic if you have a really large graph. These are expensive to train. Do you want to be doing this again and again all the time? And so what do you do instead? That brings us to GraphSAGE. GraphSAGE is a different technique for creating an embedding. And what you do is it's basically 3 steps. It's sample. So just like we talked about with Node2Vec, you take random walks in the neighborhood of your nodes. But GraphSAGE is built to work on node properties. So what you want to do here is you're going to aggregate the properties of those surrounding nodes in your neighborhood. And then you're going to make a prediction. You're going to fit a loss function based on those node properties to come up with your graph embedding. And because you're fitting a loss function, what you're really doing is you're training a predictive model to predict your embedding. And so what's exciting here is when you add new data, you have that model that you fit. And you can just calculate an embedding by applying that model that you trained. It's an inductive approach. So you can train the model on one part of your graph and apply it to a different part. Or as new data comes in, just apply that trained embedding model to the new data and you get your embedding. So GraphSAGE is really cool if you have a lot of properties and if you have a dynamic graph where you don't always want to be retraining. So the kind of TLDR of why do I do embeddings is they're a super powerful way of doing feature embedding. So rather than running a whole bunch of algorithms that describe specific aspects of your graph, so I want to make a fraud prediction model, I want to run PageRank and betweenness and Louvain and node similarity, because I think those 4 things are important. What the embeddings do is they learn a unique representation of your graph and they figure out from your graph for your problem what's important and translate that into a way that you can use it to make predictions. So you have your giant adjacency matrix, condense that down into lower dimensional space, use that to make predictions and improve your models because you're not reasoning about specific aspects like PageRank or betweenness centrality. You're reasoning about your whole graph topology and you can make predictions. So it's a pretty cool technique. Kind of the secret sauce to how Neo4j does things so quickly and so flexibly is the graph catalog. And so what the graph catalog is, we talked about Neo4j, the database. It's native graph storage, store your graph data in a graph shape. In order to run graph algorithms, you're going to project that data into a computational graph. And what this is it's a Neo4j internal technique to load the data you want to analyze into memory, into a structure that's optimized for these massive global iterations. And when you do this, you can select the subset of data that you want to load. So I have a graph of people, places, and things. I only want to run my algorithm on people and places. Or you can transform your graph. You can transpose your data. You can change direction. You can aggregate things. So maybe I have people, places, and things. I load that into memory, and then I collapse it. So I connect people to each other based on common places and things. Or maybe I have multiple relationships between people and places, and when I project it into memory, I just want a single relationship, but I want it to have a property that's the count of how many individual relationships there were. So you can transform your graph automatically for fast iteration, layering, and it's highly parallelized. It's got enterprise support, so it's a really clever way of taking your kind of source of truth and transforming it into different experiments, different slices, different subsets, different permutations to reason about it, to make predictions, and to figure out what's the right structure for your use case. So if we talk about machine learning on graphs, right? I said connections are important, relationships make better predictions. Let's go back to kind of high-level machine learning. If you think about how you kind of group machine learning, you have unsupervised techniques, which are unlabeled data. What you're doing is data-driven. You're looking for patterns. And you have supervised techniques where you're predicting something. You have labeled or categorized data, and you want to predict a number or a category. And it's really task-driven, and you have a thing that you need to predict. And so if we think about graph algorithms, kind of the traditional things I talked about, really those fall under unsupervised machine learning. Your community detection algorithms are basically clustering. Similarity and pathfinding are a graphy way of doing association. Centrality algorithms, or some of your embeddings, are basically unsupervised dimensionality reduction. I want to figure out how important each node is. And so up until the last release, Neo4j really focused on unsupervised techniques. Find patterns in your data, extract them, enrich your data set. What we've introduced in our most recent release is supervised machine learning, or ways to reason about labels and make predictions in the graph. And so if we talk about supervised machine learning, really what we're saying is you want to use labeled data to learn a function to map input data onto outputs. So in my like toy example we've all seen before, you have images, they're labeled as cat or dog. You pass those to a model. Maybe your images are encoded as pixels, you've got some kind of image embedding. You fit a model that can take those images and predict this is a cat or this is a dog. You learn a function to transform the input into a prediction. Once you've trained that model, you can give it new data. So I have a mystery image and I say, model, is this a cat or a dog? And you predict this is a cat. The way that you know if your model is any good is you hold back some data and then you measure its accuracy. And there's lots of different performance metrics, but basically the idea is, can I make, I know what the label should be. Can I decode what the label is? And I want to measure if my predictions are any good. When we talk about supervised machine learning in a graph in Neo4j, there's really two things you can do. So if you think of your graph as your labeled data, what do you have? You have nodes they have labels. Remember, we talked about each node has a type. And those nodes are either connected to each other or not. They either have a relationship or they don't. The features that you have in your graph may be pre-existing attributes, data you loaded in. So if we have our graph of retail transactions, you have items attached to those item nodes. Maybe you have a price. Maybe you have number of items in stock, the number of items that were sold in the last year, how much it costs to order that item, and how much you sell it for. Those are tabular attributes that are associated with each of those nodes and their features. Then you can enrich that data set with your graph algorithms. You can add new attributes, new features to your graph based on knowing what you're looking for. So I think PageRank is predictive. I can run PageRank. I now have a PageRank property on each node in my graph. And then finally, you can use those embeddings, those cool custom representations of your data for your use case. You can calculate embeddings for your nodes and use those as features. So what can you predict? What labels do we have in our graph? There's two things. The first is node classification. So what label should this node have? What kind of node is it? Maybe I have a transaction graph and I want to know who's committing fraud. Some nodes have been labeled as fraudsters. Some nodes have been labeled as innocent. And I want to predict for an unlabeled node, what type are they? What kind of node is this? Then you have link prediction. Link prediction is really, given a pair of nodes, should there be a relationship between them? And the labeled data you have is the relationships that are there and the relationships that are not there. So diving a little bit more into each of these use cases, let's talk about how you train a node classification model in Neo4j. So what you're doing is you're predicting a node label or a categorical property. You're going to load your data into your in-memory graph with the labels and features, and you're going to basically specify the property you want to predict and the features you want to use to make that prediction. So I've got my graph of retail customers, and I've loaded in customers that are loyal and customers that are at churn risk and customers that I don't know about. And I've calculated the page rank of those customers, the number of items those customers have bought, as well as the topology of the graph with an embedding. I say that I want to predict who's going to churn, the is churned property, and the features I want to use are my page rank, my tabular values, like how long this user has been a customer, and the embedding. And then you basically say node classification.train, and it outputs a predictive model. And so Neo4j really does the tricky parts for you. We split your data for train and test. We build a whole bunch of logistic regression models using the data you've specified, kind of the subgraph you've specified, and the parameters that you've passed to us to train your models. And then what we return is we evaluate the accuracy of each of those models against your data, and we return the best performing model. So then you have a model object, and you have your, going back to our retail graph example, customers who churned, customers who didn't churn. But then you have a lot of customers who you don't know if they're going to churn yet. They're unlabeled. You can apply that predictive model to those unlabeled nodes and make a prediction. So enhance your data with new predictions, new information about what's going to happen. Link prediction is a little bit more complicated. And what link prediction is, instead of predicting a label, you want to predict either edges that are going to form in the future. So let's say I have time series data and I have a knowledge graph and I have facts. Maybe I want to predict facts will learn in the future. Or maybe I want to do something like, I think my data is incomplete. I'm missing edges. They're already there. I just don't know about them. I want to complete my knowledge graph with the missing data. And so what you do is you load your in-memory graph with the labels and the features. So maybe I have a graph of genes, chemicals, and diseases, and I want to predict new chemicals or drugs that are going to be associated with diseases. I load that gene, chemical, disease graph into memory, along with maybe I calculate some features like page rank, like the hub score or the Louvain community. And I calculate an embedding. Then I kind of already have my data. I have my relationships that exist, and my negative examples are just the relationships that aren't there in the graph. Neo4j, again, does the hard stuff. So we take that data, you use our split relationship procedure to split your graph into train and test, and then you use link prediction.train. And again, you're going to build a bunch of logistic regression models using the data that you specified as your features over a range of parameters that you've specified. We evaluate the accuracy or the performance of each of those against the test data, and we return the best performing model. Then you can apply that to your graph to predict new relationships that you haven't observed yet. So both of these are about using those algorithms, using the properties you have, and using the embeddings to make predictions to train a supervised model. What's super important to be able to do that, though, is having models in Neo4j. So we've added the concept of the model catalog. So when you train a model to make predictions on unseen parts of your graph or new data, you have a predictive model object. And if you're used to Python, maybe you've used a pickled model before. What this is it's a model object that lives in the Neo4j database. It lives in the analytics workspace in a model catalog. And we store information. We're a database. We're really good at this, about those models. So what data was this model trained on? What type of model is it? When did you train it? What's its name? And we let you persist those models, store them to disk, publish them so you can share them with your team, so that if you restart your database or it's knocked over, that model survives. So I spend 4 hours training GraphSAGE. I don't want to lose it in case my database restarts, so I'm going to persist that model to disk. If I restart my database, I just load it back again. So we store all these machine learning models that you've trained in the analytics workspace so you can leverage them and apply them to new data or unseen parts of your graph. So what does this make possible? It really makes it possible to do graph machine learning entirely within Neo4j. And the idea is, we want to reduce the friction. If you're a graph expert, you're super savvy, you've done this for decades, you probably already have a Python pipeline. That's really cool. We've got Python drivers to support you. But what we want to do is make it easy to get started. So you can use the algorithms for graph native feature engineering, run queries, run algorithms, run embeddings. Then you train your predictive model using our ML procedures. You specify the model type, we do the property selection, the test train splits, the model selection. And then you have that model in Neo4j. You can apply it to new data that comes into your graph or unseen data that your model wasn't trained on. And then use it for predictions or decisions or enhancing your graph. Or you can store that model in the database to use it for later, then publish it to share it with your team. So what does this look like in the real world? We really talk about it as a spectrum, going from simple ad hoc one-off questions to highly repeatable production workloads, and kind of complexity, going from I want to run an algorithm to answer a question to I'm going to train a super bespoke model for a really important business critical use case, really R&D forward. And we really think about simpler complexity, less repeatable as being graph analytics, where you're running algorithms or queries to answer questions. And then we think about more complex use cases where you're making predictions, running ML pipelines as data science. And there again, they're a spectrum. They're not one is exclusive of the other, but I want to highlight just a couple customer use cases to show you that what I'm talking about isn't just interesting words or hand waving, but stuff that's done in the real world. So Boston Scientific is a great example of graph analytics in practice. And so they're a medical device company. They have a really integrated supply chain going from raw materials to finished products. Their finished products are things like heart valves and stents. So failures are really bad. What they've done is they've stored that whole supply chain from raw materials to finished products in Neo4j. And so they see which parts go into which other parts. And what they do is when they see a failure, they use the graph, they run algorithms like centrality and PageRank to rank nodes based on their proximity to failures to find vulnerable components so they can intervene before that failure cascades to other products in their graph. Or they run algorithms like similarity to figure out, okay, this node that had a failure is most similar to this other product. I should intervene before something goes wrong. So they have a question, they run an algorithm, and they answer it. AstraZeneca is a great example of what I call graph R&D, improving patient outcomes. What they have is medical records stored in a graph where you have each patient's journey through the hospital system. For every patient, you have visits to the doctor, procedures they get, diagnoses, maybe prescriptions they've received as a time series. They extract that time series data and they train a path embedding. So different than what I talked about earlier, but it represents each patient's journey. And they use those embeddings to predict which patients will benefit from a new drug that they're bringing to market. And so this is really sophisticated R&D, right? They trained a custom embedding in Python. They apply it to billions of nodes, and they make predictions. And kind of in the sweet spot between those two is where we talk about production graph machine learning, which is something we actually see a lot of in the financial services space. And what they're doing is they're adding predictive relationships to production ML pipelines. So they know these features are predictive, they've trained a model, they need to retrain that model, and they need to score incoming data. And so every percentage point of accuracy matters. Graphs are important, but they use Neo4j to be able to reliably generate those features and export them to their ML pipeline so they can make those predictions over and over again in a reliable, repeatable way. And so taken together, when we talk about Neo4j for graph data science, it's not just one thing, right? It's the graph algorithms, it's graph native machine learning, things like supervised ML in the graph. It's our ability to scale into the billions of data points. We're extensible, we integrate with your sources and your ML platforms. And we try to have a humane, friction-free experience with a strong, welcoming community. Hopefully this is exciting and you'll be interested in following up with some resources. We've got some easy ways to get started, some books you can read. We also have a session coming up from Neo4j around building knowledge graphs, as well as a demo with Stuart Laurie around some of the techniques I talked about today. And so with that, I'll take any questions. Thank you so much.